Magnetic resonance sequences today. So we have discussed already that MRI is a diagnostic modality in which magnetic resonance, MR active nuclei, RF pulse and computers are used to generate the MR images in the transverse, coronal, sagittal and any oblique planes. An MRI sequence in magnetic resonance imaging is a particular setting of pulse sequences gradients resulting in a particular image appearance. A multi-parametric MRI is a combination of two or more sequences and or including other specialized MRI configurations such as spectroscopy. The basic of MRI physics is the magnetic characteristic of an atom, and they are electrons orbiting the nucleus spinning but very less as comparing to protons. Protons spinning on their own axis and nucleus itself spinning about its own axis. So we know that these are the motion characteristic of an atom. In an atom there are electrons in the orbitals and protons and neutrons in the nucleus. So this electrons orbits around the nucleus and then and it spins also but very less in comparison to the protons, and the protons spinning on their own axis and the nucleus itself is spinning about its own axis. So these three particles which are in different types of motions we are taking advantage of these characteristics in forming an image. So the MR active nuclei, those nuclei which have odd number of protons are called MR active nuclei. They behave as tiny bar magnets as protons and neutrons spins about their own axis within the nucleus. Even mass number nuclei, there is no net spin. That is why they are not MR active nuclei. So it cancels out each other as we know it. And odd mass number, they possess a net magnetic spin, and hydrogen is abundant in human body. Hydrogen is MR active nucleus used in MRI. So we have seen previously also some important MRI active nuclei. So hydrogen, it has a spin quantum number of half resulting in a gyromagnetic ratio of 42.6. Carbon again half, gyromagnetic ratio 10.7. Oxygen spin quantum number is 5/2 and gyromagnetic ratio is 5.8. Fluorine half, 40. Sodium 3/2 spin and gyromagnetic ratio 11.3. Magnesium has a spin quantum number of 5/2 and gyromagnetic ratio of 2.6. Phosphorus half and GMR is 17.2. Sulfur has spin quantum number of 3/2 and gyromagnetic ratio 3.3. Iron has spin quantum number 1/2 and GMR of 1.4. So any nuclei which possesses a net spin quantum number can be, or odd number of quantum numbers can be used for this purpose because there is a net spin. NMR is technique for investigation of chemical and physical properties at the molecular level. So the word magnetic uses the external magnetic field to interact with nuclear magnetic moments, and resonance exploit resonance to perturb nuclear spins, and imaging vary the external field as a function of position to localize signals. So in the previous class we were discussing that these are the characteristic of the atoms or the nuclei in the atoms in our body. So there is a net magnetic field in our body, and when and in the MR machine we have a magnetic field. When our body is placed in the magnetic field, the magnetic dipoles get aligned. It can be in the direction or in the opposite direction. So once it is getting aligned, we apply a resonant frequency, and the resonance that will alter the magnetization of each of these things, and when it relaxes, it builds or relaxes. Based on that, we get some information about how each of the atom or the nuclear vectors inside the body behaves with the given signal. So that information we are coding into the electronic circuitry and the computer system, and we are doing an image processing through which we are getting an image which can be identified or understood by human eye. So the NMR, the initial NMR is what is developed into MRI. So alignment of protons, we have seen when no electric field is applied, proton nuclei have random motion, and under the application of magnetic field, dipoles align in two states, parallel or anti-parallel. Those who have low energy, they will get aligned in the parallel direction, and those who have higher energy, they get aligned in the anti-parallel direction. And the net magnetization vector, if dipoles are aligned in excess in low energy direction in contrast to high energy, direction of this net excess is referred to as net magnetization. So here you can see 3 protons are aligned in the parallel direction and 2 are in the anti-parallel direction. So we have a net magnetization in the same direction as the applied magnetic field. So resonance, it is an energy transition occurs when object is subjected to frequency same as its own. In MR, resonance is induced by applying an RF pulse at same frequency as of preceding. Hydrogen nuclei perpendicular to the applied magnetic field, which is B0. So you can see that the net, it has a net magnetizing spin, and when the RF pulse is applied at the same frequency as the spinning nuclei, we get a resonance from it. So that is what is shown here. And the Larmor frequency is the speed at which magnetic moment wobbles about external magnetic field, and it is called a precessional frequency. Larmor frequency is used to determine precessional frequency for a specific nucleus. So that is W equal to gamma into B0, where W is the precessional frequency, B0 is the applied magnetic field, and gamma is the gyromagnetic ratio. Is precessional frequency of a specific nucleus at 1 Tesla, and unit is megahertz per Tesla. So we know that hertz is the unit of frequency and Tesla is the unit of magnetic field strength. So precessional frequencies of hydrogen used in MRI are 21.285 megahertz at 0.5 Tesla, 42.57 megahertz at 1 Tesla, and 63.86 megahertz at 1.5 Tesla. And precision, compound motion of a rotating object about an axis other than an axis of rotation is called precession. So if any motion other than the axis of rotation is called the precession. So every MR active nuclei, due to influence of external magnetic field, produces secondary spin or spin wobble. So the wobble is known as precession and causes magnetic moment to describe a circular path around the magnetic field. So you can see this circular path or the wobbling of the nuclei. That is what, in addition to its actual spinning about its own axis, is called the precession. And a free induction decay or FID, when the RF pulse is switched off, the NMV, nuclear magnetic vector, is again influenced by B0 and it tries to realign with it. So in order to do so, NMV must lose the energy given to it by the RF pulse, and as relaxation occurs, the NMV returns to realign with the applied magnetic field B0. And pulse sequence is a combination of RF pulses, signals, and intervening periods of recovery. The pulse sequence consists of several components. TR is repetition time. It is the time from the application of one RF pulse to the application of next and is measured in milliseconds. TE is the echo time. It is the time from the application of the RF pulse to the peak of the signal induced in the coil, measured in milliseconds. TE control the amount of T2 relaxation that has occurred. So some of it might feel like a repetition, but these are very important for you to understand. That's why I have included again in the slides. So we have seen what is TR and TE. So from the beginning of the RF pulse to the beginning of the next RF pulse. And here TE is the beginning of the RF pulse to the RF pulse to the bottom of the signal. That is the TE and TR. And we will come across the term T1 recovery. It is caused by nuclei giving up their energy to the surrounding lattice. So it is often termed spin lattice relaxation. The rate of recovery is an exponential process with a recovery time constant and is called T1. This is the time it takes 63% of LM to recover in the tissue. So you can see this pictorially also. As the RF pulse relaxation takes place, the T1 starts to get back or get aligned itself to the applied magnetic field. So the relaxation takes place. So you can see that the horizontal pink arrow is reducing in size and the vertical red arrow is increasing in size with each step, with time. At time 1, time 2, time 3, you can see the pink arrow is further reduced and the red arrow is further increased, and finally there is no pink arrow and only the red arrow. So that is what it is. So this signal, the increase in the signal strength is depicted in a graphical form with time. So 63% of it is, that time is called the T1 relaxation or T1 recovery time, or the spin lattice relaxation time. From this picture, I think you can understand very clearly the RF signal is relaxing here. It is reducing and the net magnetization vector in the applied magnetic field increases, and that is what it is. So 100% is with the time instant 4. So with respect to the time, we plot a graph. So when it is 63% is recovered, that corresponding time is what is called T1 recovery. So we have discussed this before also. So the T1 recovery in fat and water varies, and this occurs due to the nuclei giving up their energy to surrounding. That is the same. It gives up its energy to the surrounding. Slow molecular motion in fat allows the recovery process in fat is rapid. And T1 time of fat is short, but in water it is long. So when it is fast, the time is short, and when it is slow, the time is larger or longer. So you can see that here it recovers faster, and it gets back closer to the longitudinal magnetization faster. And here you can see it is slow. So with time, how much it gets back to the longitudinal magnetization, that is again less. So as time increases, this will become slowly flattened out. So if it happens in a short interval of time, so in this period of time only it is increasing and coming close to the longitudinal magnetization. And T2 decay. T1 it is recovery and T2 is the decay. So during the relaxation, the magnetic movement of the NMV loss transverse magnetization due to dephasing. The relaxation results in decay of magnetization in the transverse plane. The decay of transverse magnetization is caused by the process termed T2 decay. It is often termed spin-spin relaxation and results in decay. There it was spin lattice relaxation, and here in T2 it is spin-spin relaxation. The T2 relaxation results in loss of Tm due to interaction of the magnetic fields of the adjacent nuclei. A signal or voltage is only induced in the receiver coil if there is a magnetization in the transverse plane. So with respect to time, how much is the difference? So in EXY is in the transverse plane. So with respect to time and longitudinal magnetization, percentage of longitudinal magnetization and transverse magnetization, you can see how with respect to time the longitudinal magnetization varies and the transverse magnetization varies. So the transverse magnetization, the loss in magnetic moment is T2 decay, and in the longitudinal magnetization gain is called T1 recovery. So correspondingly, what happens along with time is what we are seeing here. T1 contrast, T1 time of fat is shorter than, please mute yourself if you are outside so that it doesn't disturb others. T1 contrast, it is T1 time of fat is shorter than water. Fat vector realigns with B0 faster than water. Longitudinal components of magnetization of fat is larger than water. So this may be little confusing and you might tend to forget or complicate it. So at least focus on one thing, whether it is faster or magnetization decays or all that. So with respect to fat, with respect to water, so what happens? One parameter you remember for T1 and T2. So the correspondingly the other parameter also vary and it will also be different for T2. So that way you can remember it and reproduce it better. So T2 decay in fat, it occurs as the result of magnetic fields of nuclei interacting each other. Energy exchange is more efficient in the hydrogen in fat. The T2 time of fat is short. So that is what is expressed in the graph here. The transverse magnetization, fat loses transverse magnetization rapidly, and the fat vector in phase and the D phase is shown in the circular, the phase and D phase is shown in the circular this thing, and the magnetization is shown in the form of graph. So T2 it is decay and T1 it is recovery. So T2 decay in water, energy exchange in water is less efficient than in fat. So T2 time of hydrogen in water is long. T2 time of water is around 200 milliseconds. So T2 contrast is T2 time of fat is shorter than that of water. So transverse components of magnetization of fat decays faster. Water has high signal and appears bright on T2 contrast image. Fat has low signal and appears dark on T2 contrast image. So how the signal will be with respect to magnetization as well as the phases. So here it is less steep compared to here. Here it is more steep. Here it is less steep. And fat vector defaces quickly. And here the vector defaces slowly. And proton density contrast, it is the difference in signal intensity between tissues of their relative number of protons per unit volume. High signal will be bright on proton density contrast, and the tissue on low proton density have low signal, that example bone, which will see dark on the proton density image. So proton density is the basic of finding the contrast in MRI image. And image acquisition, waves transmitted from the system needs to be collected before they disappear, and it is done by receiver coils, and coils should be placed perpendicular to the applied magnetic field B0, and coils are made up of copper. So this is how the different coils look like: head coil, surface coil, shoulder coil, spine coil, neck coil, and knee coil. So this is again how the excitation, relaxation, and the resonance signal from that will be received by the coil which is placed near to the body part which is being imaged. That image will be compared with that signal, that the RF signal which is received back will be compared with the RF signal and the other parameters which were there already. So that will give rise to an image which can be viewed. So we have seen this before, the components. So there is the magnetic board and the RF coils and the gradient coils, shim coils and magnetic coils. And there is power supply to the magnet, power supply to the shim coil, the gradient, the receiver coils are also there. So the resultant from the RF coil, the resultant from the gradient amplifiers are fed into the host computer, and the operator so this has, the host computer has information received from the receiver coils as well as the input coils, power supply, the magnetic field strength, the net magnetization vector, all those things. The net magnetization vector information we get from subtracting this information. And so whatever signal we receive, that we process in the image processor, and then we will get the image in the visible form. The components of MR imaging system, we have seen, we have a magnet, we have RF wave, we have image processor and computer system if we classify them broadly. So the permanent magnet consists of material which has been magnetized such that it won't lose its magnetic field. The materials such as iron, cobalt, nickel, etc. are magnetized, placed in the high magnetic field for a longer period of time so that it gets magnetized, and then but to the power to which the magnetic strength can be increased is very low in permanent magnets. So the magnetic strength of permanent magnets is in the lower range, 0.2 to 0.3 Tesla. Advantages are low power consumption, low operating cost, and no cryogens. So there is no power consumption because the magnet is already magnetized. And there is no operating cost because we don't need to produce any magnetic field. It is already there. And no cryogens are utilized. Cryogens are used for cooling. We have discussed this. So these are the advantages when we talk about permanent magnets. Disadvantages are limited field strength. The maximum field strength which can be achieved for a permanent magnet is of the order of 0.3 Tesla, and it's very heavy. And electromagnets, it uses electromagnetic induction, that is by passing electric current, magnetic fields are produced. So resistive coils, magnetic field is generated by a current which runs through loops of wire. These can be air core or iron core ones. And iron core, a current is surrounded by a magnetic field that can be used to induce magnetism in iron. Magnetic field strength, it has a magnetic field strength and is of the order of 20 kilogram of iron. And the disadvantage is high power consumption and temperature stability size. And air core, current carrying conductors can be configured to produce desired magnetic field with desired uniformity. So magnetic field strength is 0.2 Tesla. Disadvantage is large power supply and power supply regulation requirements. And advantages are easily produced and low cost, both of this. And superconducting magnets, this is the thing which changed the scenario for MRI imaging. Large number of metals or alloy loops of traces of resistance to current flow when cooled to absolute zero. So NBTI used material, niobium, titanium used material in the form of wires in copper tubes. So coolant in the form of liquid helium is used to reduce the temperature. So the advantages are high magnetic field. We can achieve up to 12 Tesla strength and low cost. Coil is an electrical device which is composed of loops of wire that can either generate the magnetic field or detect a changing magnetic field as an electric current induces in the wire. Different types of coils are used in MRI. We have discussed that before, but still we will go through it again. Shim coils, which correct field inhomogeneity around the bore of the magnet. It produces magnetic field homogeneity caused due to uneven spaced coils of wire. It creates magnetic field homogeneity. This process is, and the process of achieving the magnetic field homogeneity is called shimming. And radio frequency coils, short bursts of some electromagnetic waves are transmitted at resonant frequency of hydrogen. We need a special RF pulse that can exchange energy with the protons. Energy exchange is possible when protons and RF pulse have same frequency. RF coils can be transmitter or receiver. Transmit coils are body coils, head coils, and they can they can be transceivers, surface coils, or phased array coils. So we have seen these. The gradient coils, they are set of coils provides a slope of magnetic strength from one end to another, which is achieved by passing current through it. Powered by gradient amplifiers, by varying magnetic field strength, it provides position-dependent variation of signal frequency. Used for slice selection, phase encoding, and frequency encoding. So these are the pictures. So in the first row, only the gradient coils are shown and X gradient coils. And in the second image, the Y gradient coils and the Z gradient coils in the third image. So when all three are superimposed, it will look like this. So each are perpendicular to each other and the applied magnetic field. Coming to image reconstruction, the gradient coils and encoding. So here you can see the different protons in the applied magnetic field and its gyromagnetic ratio. So 63, the frequency as well as the gyromagnetic ratio. So 63.6 megahertz, how it looks like. So at different phases with respect to the applied magnetic field is applied. And slice encoding is, here you can see that previously it was all at 63.6 megahertz and here 63.5, 63.6 and 63.7. So you can see that the variation, what happens with that, and correspondingly the phase information. So when the RF pulse is relaxing, it will give, the RF pulse will be applied at the same frequency as the precessing nucleus, and that is applied. Then those took different phases. So those which was in 63.5, it is here, 63.7 hertz, it is there. Then it start relaxing. So when it relaxes, we have two information. Same frequency ones becomes same phased ones. So the nucleus which is in the same phase will have the same frequency and same phase. So this circle which you are seeing, the darkest part, that is the phase of both of this. So it is represented like this. You will get a better, clearer idea by seeing this. So here you can see. Yes.
Ma'am, here we are applying gradient coils now. By applying gradient coils, we are creating gradient field.
Yes, yes.
Okay, ma'am.
So here you can see, X coils, Y coils, Z coils. Each of the K coils will give different signal information. So by these coils are helping to get the information about the frequency as well as the phase of the magnetic nuclei in each of the phases in the magnetic relaxation process. So here you can see, when you see all of that, you will get a clearer idea. So here the same frequency, same phase. You can see the nucleus with its rotation as well as the GMR. Then the phase is represented like this. So, sorry. So when we come here, so this is the gradient. It varies from minus GZ to plus GZ. We have seen like it varies in the range of 500, 560, 580 like that. From minus that to plus GZ. So here you can see another one. And how the phase changes when it moves. So this one, The phase is represented by the shaded arc of the circle, and this is the nucleus. So this is another but different phases. Same frequency but different phases. Here it was same frequency and same phase. Here it is same frequency but different phases. And here it is different frequency and different phases. You can see that the gradient phases are also changing with respect to the nucleus which we are considering. So each nucleus, when it is getting magnetized and when it is getting demagnetized, we get information about its frequency as well as phase. So when we superimpose all this information, we have a mathematical resultant page, something like this. We have the final resultant phases as well as the frequencies, which are, so this information is according to the, and we know which coil contributed to what. So which nucleus have what, that information we have from this. So we have a resultant final result like this corresponding to phase and frequency. The GZ gradient selected an axial slice, GY gradient created rows with different phases, and GX gradient created columns with different frequencies. So we got the X, Y and Z information about the nucleus with respect to its frequency as well as phase. So gradients are coils of wires that when current is passed through them alters the magnetic field strength in a controlled way. So we know how much current is passed, so how much alteration is happened with respect to each nucleus. They add or subtract from the existing field in a linear fashion, so the magnetic field strength at any point is known. When gradient is applied, the field strength at isocenter remains unchanged. At certain distance away from the isocenter, the field strength either increases or decreases. So magnitude of change depends on distance from the isocenter and strength of the gradient. So that is what was seen here. This is the gradient. These two triangles which we are seeing. This. So this is actually isocenter. Like we have x-axis, y-axis. So in the positive direction it increases, in the negative direction it decreases. So this is the gradient phase. So from isocenter, at what distance and at what strength, this information we get. You understood all this, no? So that is what is happening. When the gradient is applied, the field strength at isocenter remains unchanged, whatever phase it is, whichever direction. And at certain distance away from the isocenter, the field strength either increases or decreases. And magnitude of change depends on the distance from the isocenter and strength of the gradient. So this is a three-dimensional process but represented in a 2D picture. So you have to imagine yourself in the three-dimensional, that's all. The strength or amplitude of gradient is determined by the amount of current applied to the gradient coil. So for large current, gradient is steep and therefore change in field strength over distance is greater. And for small current, gradient will be shallower and the change in field strength is smaller and vice versa. When more power is given, faster or steep gradient we will have. So like if we have a steep this thing, the difference with respect to time will be greater, no? I think. Yeah. So We will come to that. So if it is steep, the change will be greater, and if it is shallower, the change will be lesser with respect to distance or position of the nuclei. So the precessional frequency of magnetic moment of nuclei is proportional to the magnetic field strength experienced by them. And along the position where gradient applies, the precessional frequency is changed, which is received by the patient. So, like if we take B at 1 Tesla, point A, 0.9995 Tesla, and point C, 1.0005 Tesla. So this is in the positive direction, this is in the negative direction. And polarity of gradient, it determines the end where gradient produce higher field strength than isocenter, and where gradient produce lower field strength than isocenter is negative. Polarity is determined by the direction of current flowing through the coil. Imposing a gradient changes field strength in linear fashion across a distance in the patient. Precessional frequency of magnetic moment of nuclei in a linear fashion. These characteristics can be used to encode the MR signal in 3 dimensions. For this, 3 orthogonal sets of gradients are situated, which is bore of the magnets. So orthogonal means each are perpendicular to each other. So we have 3, all 3 are perpendicular to the applied magnetic field. Z gradient alter magnetic field strength across Z axis, Y and X along Y and X respectively. So the gradient used for each task depends on plane of scan on which gradient operator selects to perform frequency or phase encoding, and slice selection locates the slice in the scan plane selected, and frequency encoding locating a signal along long axis of the image, and phase encoding by locating the signal along the short axis of the image. So these are the 3 things majorly the gradient is used for: slice selection, frequency encoding, and phase encoding. Frequency encoding is done by the long axis and phase encoding is done by the short axis of the image. So the when we talk about the slice selection, gradient alter the magnetic field strength of magnet linearly. The magnetic moment of nucleus within a specific slice location along a gradient have a unique precessional frequency when gradient is on. Hence, a slice can therefore be selectively excited by transmitting RF at that unique precessional frequency. So the gradient is applied. Each nucleus has a unique frequency, and an RF is applied at the same frequency as the frequency of the nuclei. Slice A cannot be resonate with 63.86 MHz because they are spinning at different frequency. Z gradient selects axial slices, so nuclei in the patient head differs from those in the feet due to spinning at different frequency. Y select coronal slices, so nuclei at back of patient spin at a different frequency from those at front. X selects sagittal slices, so nuclei on right hand spins at different frequency from those on the left hand side. A combination of any 2 gradients selects oblique slices. So in order to get axial slices, we take information from the Z gradient coil. In order to get the coronal information or coronal slice, we get information from the Y gradient coil. And for sagittal slice information, we use the X gradient coil. And if we want to have a cut on an oblique plane, or we want an oblique slice, then we use combination of any of those two. So depending on how much the combination is, depending on that, we will get varying oblique angles. And slice thickness is determined by slope of slice select gradient and transmitted bandwidth. Slope of the slice select gradient and transmitted bandwidth. Thin slice requires steep slope and narrow transmit bandwidth and improves spatial resolution. When we have a thin slice, so for that we need steep slope, like steep gradient, and narrow transmit bandwidth. So you can see here, if you remember the focal spot size in X-ray, this thing, same thing. So when we have a steep gradient, we get a thin slice. So the corresponding bandwidth. So when we have a shallow gradient, we have a thicker slice. And this is given for a particular bandwidth. So we can increase and decrease this bandwidth also. Like if we take this particular one, steep gradient, if we further reduce this, the slice thickness will further reduce, right? The transmitted bandwidth is brought down, the slice thickness will further reduce. So here also, if the transmitted bandwidth is brought down, the slice thickness will reduce. But when compared to a steeper one, it will be different. So with a steep gradient and with a shallow gradient, the bandwidth for the slice thickness for the same bandwidth is shown here. So if we increase the bandwidth, the thin slice thickness will increase. If we decrease the bandwidth, the slice thickness will increase. And phase encoding, for that the slice is selected. Spatial location of spins with the slice is determined by using the gradient. And when gradient is switched on, precessional frequency is determined by its physical location on the gradient. I think we will stop for today here and discuss phase encoding from tomorrow. Can we have a class tomorrow?
Yes, ma'am, but at what time?
6 o'clock? Same time? Today's?
Ma'am, can we have at 2 o'clock tomorrow?
2 o'clock. We can try for 2, but like I have a class from the class which is getting over at 1:30. If it gets delayed, then you will be unnecessarily waiting, no? We'll try to have it at 2 tomorrow. So be prepared for 2. If it gets, like you have a class in the afternoon after that?
No, ma'am, we are not having a class.
Okay. So it's okay, no? If we get little delayed and start at 2:30 also.
Yeah, it will be okay if it is at 2:30.
Yeah. So we can plan it for 2 o'clock tomorrow.
Okay, ma'am.
Okay. I'll share the slides. You can go through the remaining slides also. So you will get a little bit idea when we are talking about it.
साडा हक
म्हणजे